off yesterday. Yesterday we talked about decomposition means to fall apart, right? And then we said we could predict it, and the last thing we did was tear apart water, right? I let it run all period, tore it apart, and we learned that there were evidence of hydrogen and oxygen, right? We got tests that would told us hydrogen or oxygen. Are you okay with that? That's where we stopped. Okay, so what do we do? It's a binary compound. It's only got two elements, so the only way it can change is to have its two elements separate from each other. Okay, so mercury 2 oxide, when heated, sorry, is out of your way. Okay, so what elements are there in mercury 2 oxide? Mercury and oxygen. Go with the obvious answers. So mercury and oxygen. Okay, that's what decomposition says. They fall apart. Second step, write the right formulas. With these, I got elements by themselves. Got to decide, do they get a little 2 at the bottom? Does Hg get a little 2? No. Does O get a little 2? Yeah. So then I wrote the right formulas. So first I do what the name says, separate them. Then I figure out the right formulas, figure out the subscripts. Then I balance. 1 Hg, 1 O, 2 O's. So I got to fix that by putting a 2 in front of mercury 2 oxide, which gives me 2 mercuries. So I got to put a 2 there. It's okay? No. Extra super hard? Okay. And most are like that. I'm going to show you one that's not quite like that. That's this. Okay. H2O2. What the heck is that? Got an arrow. H2O2 forms, but what's that? That's our catalyst. Our catalyst is manganese 4 oxide. Okay? So it's not going to get used up. So I don't want this to be just a bunch of words on a page. So, is it working? Nope. I'm missing a camera. Let's get turned off because it's got power. It's got power. It's right here. It's plugged in. They're not in hydrogen peroxide, they're in acid. And it's about, yep. Nope, the acid doesn't burn. Flames burn. Okay, we'll talk about what's going on there in a little bit. Okay, recognized it. It's going to plug it in. Setting it up. There it is. Okay. So, I need some hydrogen peroxide. Oops, my camera didn't move. Can't see it from here. I had to turn on a camera. That tells me where it's pointed. So I pointed right there, so I'm not that far off. I just need to get to, oops, focus, stay focused. Stay focused. Okay, so got a flask there. I've got hydrogen peroxide. And hydrogen peroxide decomposes. Okay, it does so all by itself. Hydrogen peroxide will decompose. We're just going to speed it up with MnO2. The reason why you always find hydrogen peroxide in brown bottles brown plastic bottles is because light will speed up that reaction too. Light will help break the bond. So they're trying to keep light off. So if I could write the arrow and I could put light on top of it too. Okay? But as long as the light doesn't hit it, it lasts a pretty long time. Okay? But if I add some manganese 4 oxide, which is this right here, I take some manganese 4 oxide and add it in. It starts to bubble. Everybody see it's making bubbles? Okay, the manganese 4 oxide is black. It's going to stay black the whole time because it doesn't get used up. It's going to, all the stuff I poured in there is still going to be there at the end. It just gives it a surface for it to happen on and makes it a little easier for it to happen. So it's making bubbles. So our question is, what's it doing? And it's making bubbles, but what are the bubbles? Well, out of H2O2, I see 3 possibilities. It could be hydrogen, it could be oxygen, or it could be steam. Everybody okay with those 3 possibilities? That's the only ways I can think about if that fell apart and I made a gas, it would have to be one of those 3. Okay? Well, we have a test for that. We developed one yesterday. Fire. Fire was the test for that, right? So first, I can pick it up in my bare hand. That tells me it's not water. Because how do you make water into a gas? You heat it and boil it, right? This is not boiling. It's bubbling, but it's not boiling. Okay? So, yesterday we saw that if you put flame next to hydrogen, it catches on fire. But if you put flame next to oxygen, it just burns better. Right? So, let's find out. What's it going to do? Let's get a little flame going. Oops, going to get flame. That'll be enough to light that. Any guesses as to what the gas is? Everybody okay with it being oxygen, right? It's just not generating very much. Yeah, should have looked there. Used it all up. Okay, so are we comfortable with it generating oxygen? Because we got to write down what really happens. Was there any way for you to know before we did that? No, there wasn't. Okay. Okay. Then, so that's oxygen, that's O2. What else is there? Okay. Is there hydrogen? Was there hydrogen gas produced at the same time? How do you know there wasn't hydrogen gas produced? Because there was no fire shooting out the top of the flask. That would be why. Because hydrogen burns, right? So when I put that, if it was both hydrogen and oxygen, I got a big flame shooting out. I didn't get that. So it's not hydrogen. So I don't have just oxygen. What else is left besides oxygen? Water. Because that's our only possibilities, right? Out of those pieces, that's all we can make. Okay? Got to balance it. And actually, I can put a G here because I know that's a gas. Right? If I'm trying to describe it completely, yeah. Okay? So 2 H's, 2 H's. 2 O's on the reactant, 3 on the product. It's even on one side, odd on the other. So I double that. That gives me 4 H's. So I have to put 2 in front of water on the other side to get my 4 H's. That gives me 2 oxygens with water, and O2 is 4, and 2H2O2 is 4 oxygens. So it's all balanced. And that's what happens when you put hydrogen peroxide on a cut. It's the oxygen. Oxygen's actually pretty vicious. It destroys stuff. No, but it supplies the oxygen for, in World War II, the Germans were launching V2 rockets. Their oxygen supply came from hydrogen peroxide. So they decomposed hydrogen peroxide to make the oxygen to fire, to shoot it. And I think they burned kerosene with it. So they had oxygen and kerosene right next to each other. So you could have fire, so that you can shoot a rocket to England. Okay? So it's part of rocket fuel, but it's not the fuel part. It's the oxidizer. Okay. Now, if the compound has more than 2 elements, I'm going to give you one of the products. When you do the reading for 8.2, your textbook is going to talk about a whole bunch of subsets for each one of these types of reactions, where they expect you to memorize that this does this. I'm not going to expect you to memorize it. I'm only just going to expect you to be able to finish it if I give you one of the products. I mean, because the books will say carbonates, when heated, always make oxides. I give you one of the products, but it's decomposition, so there's got to be another product. And the other product will be from the missing pieces. And if you do it right, it should be really easy to balance again. Just like combining compounds, when you put them together, was really easy to balance if you did it right. Having one compound fall apart into 2 compounds should fall apart into pieces that make it easy to balance. So, nickel 2 carbonate, when heated, makes nickel 2 oxide and what's missing? Is C the only thing that's missing? There's a C and 2 O's missing. Can anybody think of a chemical? Okay, that makes sense? It should be, oh, and then we have to balance it. That was hard. Is that right?
Can you balance it again just to make sure it's right?
Nickel, nickel, carbon, carbon, O3, O3, we're done. No. Well, you can, but then you have to reduce it to the lowest ratio, which means you take the 2 back off. Otherwise, there's an infinite number of answers. And if you don't write all of them, you're wrong. Oh, as soon as you want to go bigger than the lowest ratio, then everything counts and you have to write them all down. No, and that's not possible. So we're going to go with the lowest ratio. Hey, H2CO3, aqueous, so carbonic acid, falls apart into CO2 and what's missing? 2 H's and an O. Can you think of a compound that's got H's and O's in it? What are you thinking? Okay, and then you got to balance it. 2 H's, 2 H's, 1 C, 1 C, 3 O's, 3 O's. We're balanced, we're done, life is good. This should look familiar, because yesterday we wrote this. As a combination. So how are combination and decomposition reactions related to each other? The reverse. The combination is the reverse of the decomposition, vice versa. And this affects most of your lives every day. You say, well, how could that affect my life? Okay, so a soda machine. You go to Legends and you want to fill up your cup with soda. Inside the machine, there's a hose that goes out to a CO2 tank. That CO2 comes in at high pressure into the water. And when the CO2 is under high pressure, it reacts with the water to make carbonic acid. So inside the machine, it's high pressure, carbonic acid is formed. Okay? Then you push the lever into your cup. The soda flow comes out, and now it's at low pressure. And at low pressure, the CO2 comes back out and overflows your cup with all the bubbles in your soda. So the bubbles in your soda get put there at high pressure, and when you get at low pressure, they come back out. But that means when your bubbles come out, you're destroying your acid. And that's why flat sodas taste different than carbonated sodas. Because as the carbonation leaves, you use up the acid, you use up the sour. And the sour taste goes further and further away, and all you taste is the sweet. Because the main flavors in sodas are sweet and sour. And if you lose the sour, you're just left with sweet. And that's why your soda tastes different when you've let it go flat. Now, there's still some sour, so there's other acids in there. I think there's some phosphoric acid in there as a preservative. So it's still a little bit sour. The sour's not completely gone, but all the carbonic acid part of it's gone. Okay. Really hard to do? Okay, so when you're combining compounds, think polyatomic ions. When you're tearing apart things with polyatomic ions, make sure the pieces all work out. Okay. Type number 3. Don't you like how the first two were really descriptive? Well, type number 3 is really descriptive too. Single replacement. What do you think happens, just from the name, a single replacement reaction? One thing replaces. So that means I have to have something to do the replacing, and I have to have something to replace it in. If I'm going to do replacing, I need both of those. So there's got to be two reactants. And one of them is going to be an element. One element replaces another. An element by itself reacts with a compound. So you have to have one element, one compound. Something to do the replacing, something to replace it in. And when you're done, the element that started off by itself will have a partner. And the element that had a partner will be by itself. So my products are going to be a different element by itself and a different compound using the new element. So one thing replaces another. So I need something to do the replacing, something to replace it in. So here's a pretty easy example. Sodium reacts with potassium chloride to make potassium and sodium chloride. The sodium took the place of the potassium. So potassium ended by itself, and sodium ended up next to Cl. I try to use an analogy. For 4 of the 5 different types of reactions, I can use an analogy that keeps them straight and describes what happens in them. And the analogy I like to use is dance. Okay, actually a dance. You go to a dance. Before the music starts playing, everybody's by themselves. Music starts playing, they start pairing up and making couples on the dance floor. That's just like a combination reaction. You have things by themselves. And when you started, you end up with things together. Right? Decomposition is the opposite of that. It's the end of the song. The song stops playing. You have a couple on the dance floor, well, they go their separate ways. You have one compound, you end up with two separate ones. Say, well, I don't need that for those two. Well, here's where it's going to come important is on this one. Okay? Single replacement is you're dancing on the dance floor, somebody taps you on the shoulder and says, mind if I dance with your date? And if you switch partners, you got a new person standing by themselves and a new couple on the dance floor. Sodium was dancing by itself, or standing by itself. Potassium and chlorine were dancing together. Sodium took the place of potassium, so now potassium standing by itself, and sodium gets to dance with chlorine. Okay? So it's like that was a cut in at a dance. They call that cutting in. Okay? Now, how come sodium replaced potassium? How come it didn't replace chlorine? I'm not going to be able to two metals together, but the thing that you replace is going to be like you. Right? Metals are going to replace metals. Guy's going to tap on a guy's shoulder. Girl's going to tap on a girl's shoulder, for the most part, right? Does that make sense? So metals replace metals. Non-metals, fluorine, replace non-metals. The fluorine doesn't attack the lithium. The fluorine replaces the chlorine. The things that are like each other replace each other. So it kicks the fluorine off. Fluorine kicks the chlorine off. Ends up next to lithium. Lithium's 1 plus, fluorine's 1 minus. Chlorine ends up by itself, but chlorine can never be by itself, so I had to put a 2 there. It's not balanced. I got to deal with that. So 2Fs means I got to put a 2 in front of LIF. That gives me 2 LIs, so I got to put a 2 in front of LICL. Gives me 2 CLs, which I wanted anyway. So metals replace metals, non-metals replace non-metals. Things that are like each other replace each other. Things that are like each other can end up in the same spots. Okay, so here's the same idea in pictures. Okay, sodium and chlorine, or sodium and potassium chloride. Sodium kicks the potassium out of the way. Okay. That's a replacement, right? A single replacement. Okay, it's a little bit more confusing with the fluorine twins. I mean, they're twins, right? The fluorines. Luckily for us, there are also lithium twins and chloride twins laying around. Yeah, well, chloride twins, lithium siblings. That's right.
And then fluorine comes in and just steals their
Yep. There we go. Okay, pretty simple idea. I think the dance analogy gets it, and we're going to use that dance analogy even deeper. It's going further than that. Because what you're thinking about, we're going to address. Okay. Metals replace metals and hydrogen. We're going to treat hydrogen like a metal if it's written first, right? Hydrogen's written first, it's acting like a metal. So the things that are first get to replace the things that are first. Yeah. Multiples. Oh, of course.
When you were in high school?
Oh, yeah. Well, one of them when I came back the year after because my girlfriend's, it was her prom. It's a good reason to come back, right? And you don't want to take somebody else. Not if she's your girlfriend. That sets a bad precedent for what you'll accept. So magnesium and copper 2 sulfate. Okay, so magnesium and copper 2 sulfate. You should recognize this blue color. This is copper 2 sulfate dissolved in water. This is one of the reasons why I wanted you to keep it, so I could make this. Remember I told you, keep the stuff, I was going to use it later. This is one of the places I'm using it. So that's copper 2 sulfate. Okay? Okay, and this is magnesium ribbon. Okay, a little piece of magnesium ribbon. I'm just going to coil it up so it fits in the neck. Throw it in the flask. That's very malleable. See, it bends easily. Ductile is hard to tell because I can't pull hard enough for that, but let's get this all in there. Oh, before we put it in there, let's see what it looks like before, because not everybody can see it. Okay, and after. And it's going to sit there, and sit there, and sit there. Oh, it'll be easy. You'll see. Because what's going to happen in there? Well, magnesium is going to replace what? Copper, sulfur, or oxygen? Copper. So the magnesium is going to end up next to sulfate. Okay? And copper will end up by itself. So I did what the name says. That's the single replacement. The name says single replacement. Second part, get the right subscripts. Mg is 2 plus, because it's in group 2A. SO4 is 2 minus. I don't know the charge of copper. Well, actually, I don't need to know the charge of copper. It doesn't have a charge. No, it doesn't have a charge. Copper has no charge. It's by itself. Oh, no, magnesium gave its electrons to copper. Magnesium gave its electrons to copper. Okay, now, so for Cu, when an element's by itself, all I really have to decide is, does it get a 2 or not? Okay, so it doesn't get a 2. I can add a little feature that this was aqueous when we started, right? The CuSO4 was aqueous. So then we have to balance it. That was hard. 1 Mg, 1 Mg, 1 Cu, 1 Cu, 1 SO4, 1 SO4. We're all done. So, what should happen in that flask? What should you see? You see some copper show up, and magnesium disappear. Right? The magnesium should disappear. The copper should show up. Ah, but copper should also disappear. When copper's a 2 plus ion, it's blue. I'm going to be removing that copper. I'm going to be removing the blue. And it should change whatever color magnesium is. Right? I'm going to be taking that copper out of solution. So the blue color that comes with it should go away. And whatever color magnesium makes, that's what we should get. Does that make sense? So, hard to tell from there, but if I swirl it, you'll see little clouds of, oh, you can see a little bit of copper forming. See the copper growing on the, growing right on the ribbon. So right there with the copper, everybody see the copper crystals growing right there. Okay, they're growing right on the ribbon. It's not just a bunch of letters on a piece of paper, guys. It's gonna, and it's just, I don't know, but you can probably tell this blue is a little bit lighter already. And over time, it'll get lighter and lighter, and then it will disappear. So, it's not letters on a piece of paper. We're going to see solid pieces of copper show up. See? What about this one? Okay, so zinc and sulfuric acid. Zinc's a metal. Zinc makes a positive ion, so it's going to replace the thing that makes a positive ion. And that would be hydrogen. Zinc next to sulfate and hydrogen by itself. That's what single replacement says to do. And then, second step, figure out subscripts. We know zinc is always 2 plus, and SO4 is 2 minus, so that adds up to 0. So zinc sulfate's right. And H, can H be by itself? It gets a 2. Okay, so now I've got the right subscripts, then balance. 1 zinc, 2 H's, 2 H's, 1 SO4, 1 SO4. It balances easy. They don't always balance this easy. Okay, these don't have to balance easy. I just picked a couple examples that do. But it shouldn't be just letters on a screen. So here I have some sulfuric acid. And here I have some zinc. Sulfuric acid and zinc, and it's starting to bubble.
How acidic is sulfuric?
Well, it depends on how concentrated you make it. In your the muriatic acid you buy is about 4 moles of acid in every liter. The acid in your battery is about 18 moles of acid in every liter. And it's a strong acid. So even a little bit is dangerous. Superacids are, they don't exist in water, and they're really good donators of hydrogen, the superacids. And so they can't exist in water because they'll give away to hydrogen. You give the hydrogen to water too fast. So as soon as you put them near water, they lose their acidity. Okay, so it's bubbling. What's the bubbles? Okay, what are the bubbles? Well, there's really only one way to find out what the bubbles are, and that is to catch them. And where did my catcher go? There's my catcher right here. Okay, so my equation says those bubbles are supposed to be not zinc sulfate. They should be hydrogen. And we have defined a test for hydrogen, right?
Yeah.
Is it hydrogen? Yes. Okay. Fe plus SuSO4. Okay. So Fe is a metal, so it's going to replace the metal. Fe ends up next to SO4. Cu ends up by itself. Got to figure out, so that's what the name says. I did what the name says. I did the single replacement. Second step. Little subscripts. Does copper get a little 2? No. SO4 is 2 minus. What's the charge on iron?
We don't know.
What's the charge on iron?
It has to be 2 plus.
No, if I wrote that, it would be 2 plus, but I'm not sure that's right. We don't know. They would have to tell you this one. They'd have to tell you which ion it made, because there's no way for you to know if it made 2 plus or 3 plus. Okay? Turns out it makes 3 plus. Because I know. I'm a chemist, remember? I've got a lot more learning than you do. I know it makes 3 plus. Okay? So if that's the case, then it's Fe2, SO4, 3. Right? We haven't had to fix those on the other ones because the charges added up. But now we need to do the crisscross. Okay? So I've done the second part, written the correct formulas. Now I need to balance. 2 Fe's, so I put a 2 in front of Fe. 3 SO4s, so I put a 3 in front of CuSO4. Okay, that gives me 3 Cus, so I put 3 Cus. And in case you've forgotten, it's still hydrogen. Now that one didn't whistle. Why not?
There was less.
Actually, there was more. Say, what do you mean there was more? I filled it all the way up with hydrogen,
Less oxygen.
so there wasn't enough oxygen to burn. And any oxygen that was in there, I burned out just before I flipped it over, right? That's because just before I flipped it over, I lit it, used up all the oxygen that was in there, and then flipped it over. So it couldn't burn until it touched it. And it's hard for you guys to see it, but what actually happens is it makes the flame that shoots out, and then you get to watch the flame work its way down the test tube until it, because that's where oxygen and hydrogen are meeting each other. And it just works its way down.
Can we turn the lights off?
I'll try it a bit later, but I got other stuff I want to do first. Because like that. Hey, we got CuSO4, might as well use it up, right? No reason not to. Okay, now with the magnesium, I used a big ribbon. But with the iron, that's zinc, not iron. With the iron, I'm going to use a powder. So this is powdered iron. They grind it and catch the pieces. Okay, some drops of powdered iron in there. Actually, it's not quite enough. Shouldn't be quite enough. It's mostly iron with a little bit of impurities of carbon. Okay, so this one's actually started to react already. If you look, you can see the copper sitting on the bottom because our equation says we should have copper in there, right? You can actually, this one happens fast enough you can actually see it. Why did this one happen so much faster than the other one? Okay, think about it when what has to happen. In order to react, iron has to touch copper. It can only do that at the surface. So by making it a powder, I brought a whole bunch of atoms to the surface. The same weight will have a whole bunch more atoms at the surface, so this can react faster. That ribbon, you can only go on the surface of the ribbon until that copper falls off, and then you get more surface exposed. Now, it happens so fast that you may notice that the blue's getting lighter. Because all that blue is the orange stuff at the bottom. Right? Both of those are copper. Two different forms. So if you do it enough, I don't think I have enough iron. Just a little bit short on iron. Because if I add just a little bit more iron. Oh, actually, right here, see that green color? That's how I know it's 3+. Because that's the color of the iron 3 ion. Iron 2 is orange. Iron 3 is green. No, my favorite experiment that I remember doing was where I got to use a nuclear reactor, where I got to list one nuclear reactor in my equipment list. And it was pretty cool to take your sample and stick it into the nuclear reactor, change it into a radioactive form of iodine, then you yank it back out and watch. And the half-life was about 20 minutes, so you could actually watch the amounts of radiation decline over a couple hours. Oh, it's not the most dangerous experiment. You're always working with flame and flammable stuff, so chemistry is dangerous. Okay. Actually, most dangerous stuff is probably my organic class where I was working flame next to things that were flammable. There's a problem there. Okay, think of water as HOH, hydrogen hydroxide, because in single replacement reactions, it behaves like hydrogen hydroxide, not like hydrogen oxide. What do I mean it behaves like hydrogen hydroxide, not hydrogen oxide? The metals can replace one of the hydrogens, but not both of them. So you end up with the metal taking off a hydrogen next to hydroxide and hydrogen by itself. And we can always tell when hydrogen's by itself. Okay, so water is hydrogen hydroxide. Did you get the homework too? Yeah. All right, so here's one you've done before. Well, from this point forward, pretty much all the time, because we now could talk about what we're doing, right? Hard to tell you what to do if I can't give you the name of it. Okay, so we did this. Remember, we tried the different metals, and calcium was the one where you took the piece and you stuck it in the water, and it bubbled like crazy, came out of the thing at you. Remember that? Hey, what was going on? It reacted. You saw it react. Well, calcium replaces hydrogen. So I end up with calcium next to hydroxide and hydrogen by itself. So calcium is 2 plus, OH is 1 minus, so I need 2 of them. Don't forget the parentheses. Again, that was the most common mistake, forgetting parentheses on hydroxide. And can H be by itself? No, it needs to be H2. So it's calcium and water makes calcium hydroxide and hydrogen. Now I got to balance it, 1 Ca, 1 Ca. 1 hydroxide, 2 hydroxides. See how it's easier to count hydroxides? Okay, so I do that. That gives me 2 hydrogens and 2 hydrogens. That's faster than doing 4 hydrogens and 2 oxygens. Because you'd want to leave hydrogen till the end because it shows up both. And to fix oxygen, you'd put a 2 in front of it. Right? So you end up in the same spot. But think of it as hydrogen hydroxide. Really awful? Okay. With this combination decomposition reaction, you had to assume they were going to happen. Because it's hard for you to predict whether they're going to happen. Actually, what usually determines whether they're going to happen is whether you're putting energy in or trying to get energy out. All right? But with these, you can tell ahead of time whether they're going to happen, and most of you have already anticipated why that's going to be. Because we're talking about cutting it at a dance. Okay? If a senior tapped on a freshman's shoulder, mind if I dance with your date? There's probably going to be a change. But if the freshman tapped the senior on the shoulder, mind if I dance with your date? Nothing's going to change. The senior's going to keep his date. So either way, the senior ends up dancing. Right? Well, instead of freshman, sophomore, junior, senior, there's a concept called activity. Some metals are more active than others. The most active would be the seniors, the least active would be the freshmen. No. Okay. And more active replaces less active. Less active cannot replace more active. Still going. Oh, that's the bottle of sulfuric acid, 18 molar. Sulfuric acid, 18 molar. That's how I buy chemicals. That's because glass is acid resistant. Yeah, because there's no such thing as a universal solvent, something that dissolves everything. Because if there was, you couldn't store it. What would you keep it in? Okay. All right, so here's the list. There's a list on page 266 in your textbook. You'll read about it as you read 8.2. So this is what the list looks like. At the very top, the most active one is lithium. And then they come down and there's a group. And it says these up here react with cold water, acids to replace hydrogen. Talked about the oxygen too. I'm more concerned with just the hydrogen side of this. Okay. Then I go down to the next one. And magnesium would react with steam, but not with cold water. So it's got to be heated before magnesium through cadmium will react. Water would be. But they still react with acids. If we keep going down, cobalt through lead, they don't react with water, but they do react with acids. And then right after that is H2. So hydrogen's right here. So everything higher replaces if it's an acid, that hydrogen's in an acid. But if it's water, there's got to be steam for the second tier, and the top tier will react with cold water. Does that make sense? But generally the rule is higher on the list replaces lower on the list. Is it done yet? Huh. Is it hydrogen? Yep. Yes.
So you know how like the silver, platinum, and gold are at the bottom?
Yep.
Since they're unreacted, is that why like they don't change color or tarnish?
Yeah. That's why. So at the bottom, notice it says they forming oxides only. In fact, is only indirectly, so they don't combine with oxygen. And what you see is a tarnish or a rust is that metal combining with oxygen.
So like people with fake chains, it turns green.
Turns green because it's got some copper in it, or less than pure gold. Okay. So if the element is by itself, the element by itself is higher, the reaction happens. If the element by itself is lower, the reaction doesn't happen. So I write my equation, see which element is by itself, and see if it's higher on the list or lower on the list. If it's replacing hydrogen, I got to see what state the water's in. Unless if there's acid, anything higher than hydrogen. If it's an acid, it's okay. So let's look at the reactions we did today. And I showed you that they worked. And I'll show you that in each case, the one by itself was higher on the list. So we reacted magnesium, there's magnesium, with copper 2 sulfate. Copper's down here. So if magnesium's up here and copper's down here, when I started off, the magnesium was by itself. Right? So the magnesium was by itself, so it got replaced. It happened.
Is there a trend for reactivity?
It doesn't follow a complete trend because there's too many variables going in at the same time. But you don't have to remember. You just have to be able to use this list. You don't have to memorize it. Okay. Then we did zinc and sulfuric acid, right? So zinc up here with high activity near the top, second tier. If I had put it in water, it wouldn't have reacted. But I didn't put it in water, I put it in an acid. And it's higher than hydrogen. The one by itself was higher. So the lower one ends up by itself. So in your dance analogy, seniors never end up alone. Freshmen always end up alone. If the freshman starts off alone, nothing's changing. If the freshman starts off with a partner, somebody's going to replace him. Seniors, they start off with a partner, nobody's pushing them off. They don't have a partner when they start, they're more active. They get to push the freshmen, the juniors and sophomores. Juniors end up in a couple unless there's seniors around. Sophomores are thankful for freshmen. No. Hey, so you understand it's just an analogy. It's just an analogy. You're not allowed to push someone off. It has a right feeling to it, doesn't it? It does have the right feeling, doesn't it?
Like you're telling me 6'3" guy walks
Okay. Well, I've seen some big freshmen. Okay. When I taught 9th grade in Rialto, their freshman basketball team, every single member of the team could dunk.